Hey guys,
Hello!
welcome to the second Wednesday edition of Toy Maker Television. This
Yes.
week's going to be a nice long show with all sorts of updates on all sorts of stuff.
Yes.
New format is kind of like two big updates and a bunch of little stuff. And this is a servo. And yes, Dean, we know who we are. In case of zombies, spin servo.
Right.
If you have no
Make
idea
power.
what we're talking about, go do a Google search for Hack a Week.
And
And
look at his most recent.
figure out how to make electricity with servos.
Right.
Anyway, let's get to our first project. Stay tuned. So, can you explain what this is?
Well, this is actually something you were playing around with. It's a RGB LED with different resistors for each of the different colors in this LED. And there's a transistor here, and I think you were using it to see how signals could be used to control this
I was
RGB
tinkering
LED.
with trying to build an oscillator.
Ah.
In the middle of it, I touched a wire,
And it lit up. So I thought that was really cool because it's through just capacitive, or at least I think so, capacitive touch that this light comes on. So I wanted to see if we could do this to make a mouse tracker.
So that's a 2N3904 acting as a little amplifier.
Yes, correcto.
Alright, so Addie asked if I could build a little more complicated version of this, and we'll get to that here in a second.
Yep.
Okay, so here we've got a plastic bin
Yep.
with a big copper sheet in it with squares cut onto the top of it. Each one of those squares is the same as the tip of that wire that Addie was touching. And there's a little control board down there with a whole bunch of transistors and a whole bunch of LEDs.
Yep.
And this is a proof of concept. Addie can explain what is a proof of concept for.
Right. So I used to be a behavioral neuroscientist way back when, and I worked with a lot of mice. So one of the studies that we do just to look at the behavior of the mice from their baseline is a test called open field. And that's where you have pretty much just an open field. You put the mouse in and you let it explore for, say, half an hour. Now, normally, mice will first hug the outside. And that's just because, they feel more safe. They know that one side is an area where they can't be attacked. But then as time goes on, they'll start being more adventurous and they'll start going towards the center of the field. So a lot of the ways that I've seen some labs do is by putting a camera on top and then actually tracking the mouse. And then in software, we analyze how much time the mouse has spent in different quadrants. But I actually haven't seen too many examples of using capacitive touch to analyze their movements. And so if we can find a way to use capacitive touch instead of camera, then it'd actually be much more accurate, because cameras sometimes can't focus on the mouse. They pick up light glints, or they pick up artifact, or what have you, especially if your mouse is either white or black, depending on whether or not you're in a dark room or a light room. So here we have this copper board, like Whisker said, scored into a 6x4, and in the center of each of these scored panels, I guess, we drilled a hole and we soldered a wire through that hole. And those wires all go through this plastic bin.
Let me see the back.
Yep. It's kind of a chaotic
Yeah, well, it's a proof of concept.
proof of concept. So they go through the bin and then they come out, they all come to this control board that we were talking about earlier. And these wires end up, I guess, acting as the going to the gates, perhaps, of each of these transistors to bias them. And then when a mouse touches a particular pad, then the corresponding light will show up.
Alright, let's go play with it in the dark and see if it works. Okay, we're in the dark here, and he's going to demonstrate that it works. You can see a couple of lights on there. She touches the different squares in there. different lights lit up on the board. Okay, let's grab a mouse and see if that works.
Okay.
Alright, you got a mouse there?
Yep, and I just put them in.
He'll hug the edges for a moment as he gets his bearings. Now he doesn't have nearly as much capacitance as Addy does. But you can definitely see some lights turning on and off there. So the next thing we need to do is get these amplifiers detected and turned into ones and zeros. In the places where he's able to turn a light on, that's quite a bit of energy because it's an LED that he's lighting up there.
Mm-hmm. And so that's one of the things we need to figure out is how to amp these up even more.
No, I think they're amped up more than enough. It's just a matter of detecting them with a microcontroller.
Really?
Yeah.
Okay.
Awesome. All right, let's get on to the next thing here.
Okay. So we are revisiting our variable voltage power supply. And we had a question last week from one of our commenters on YouTube about...
And we don't ignore questions, so...
Correcto. And it was about why we put the fuses in the wrong spot and why we didn't, in fact, put fuses between the ripple canceling capacitors and the voltage regulator.
Okay, so let's be clear for a safety point of view here. We didn't put the fuses in the wrong place. We put the fuses between the wall and the transformer.
Right.
Okay?
So wall,
and
transformer.
That's so that if there's a dead short in the transformer, that it doesn't catch on fire, burn the power supply down, burn the studio down, burn the cast down, burn the show down. You guys want more shows? Then we're going to keep those
Less
fuses
with the burning.
where they are, okay? We can't really do it after the regulator because this is a variable.
Before the regulator.
After the regulator, because this is a variable power supply and the current draw at different voltages is all over the map. Addy will explain that in a minute. We could put one between the regulator and the big smoothing capacitor, but honestly that regulator has a thermal protection, so if it's drawing too much current, it'll shut off anyway.
Mm-hmm. So we don't
not
have
a
to worry
huge deal.
too much about it.
But Addy's got some better explanations here.
Well, kind of. So I think of the equations that help calculate what's actually necessary in 4 different stages. So we have the wall power, which is the 115 AC, and then we have the transformer, which is 18 volts AC at 1.5 amps. That's what it's rated for. And note, this doesn't mean that more current won't go through this. It just means that past 1.58 amps, it'll blow up, kind of. So it's rated for that, but it doesn't limit it. It doesn't limit what goes through it.
Yeah, don't pull 1.5 amps through that thing. It would be bad.
Right. And so from this we go to the bridge rectifier, which I think of as stage 3. And like I mentioned before, we have this thing. It's rated for a certain RMS voltage, or maybe it's this one. Sorry. Okay, so this 18 volts is the RMS voltage, which is root mean square voltage. But once it goes through the bridge rectifier and onto the capacitors, these capacitors charge up to the peak voltage, which is past this bridge rectifier. So somehow through the magic of engineers, they figured out that you have to multiply the RMS voltage, which is 18, by 1.5 through the bridge rectifier. And what happens is you end up getting 18 times 1.5, which is 27 volts DC. And that's what goes into these capacitors, from these capacitors into the voltage regulator.
Well, it goes along next to those capacitors.
Right.
Capacitors sit between that and ground.
Right. So let me first... Okay, and then the 4th stage would be the voltage regulator. And the voltage regulator... well, let me first explain, I guess, all of these, the rest of these. So between here, we have 115 volts at X amps. okay, going to 18 volts at 1.5 amps. You solve for the missing X, and what you find is around 0.235 amps, because essentially there's like a ratio between the wall power and the transformer. So when you solve for this ratio, you'll see that in order to make sure that your transformer doesn't get more than 1.5 volts going, or 1.5 amps going through it, you need to have a fuse that is like 250 milliamps, right? And so actually that's one mistake that we made with this. I was like, oh, 250 milliamps doesn't sound like very much. So I got 1 amp. But what I actually need to do in order to protect this transformer is to get 250 milliamp fuses. That way, if more than 250 milliamps is drawn through this, then these fuses will pop.
Yeah, at 250 milliamps on the input, you'll never be going over 1.5 amps on the transformer, and that also is well within the range of what is normal for the regulator. But that gets complicated on the regulator because it's variable voltage.
Right.
You drop the voltage down to 1.5 volts, and suddenly the current that you can pull through that little sucker is huge.
Right. So, okay, so this gets a little bit more complicated. So I talked about the RMS voltage with the bridge rectifier, and that gave us 27 volts DC. Now, when you put DC voltage through a voltage regulator, especially a linear regulator, regulated one, so say you have 27 volts, right? And then output is, so let me use my handy dandy. So you have 27 volts in, okay? And then out, you have 1 volt, let's say. So the difference here is 26 volts. Now those 26 volts are released as heat. And that's apparently a lot of heat. So what we did here was we put a heat spreader on there, and you can put heat sinks, and a lot of power supplies have heat sinks as well. But then what this means is that when you do your calculations, you have to be careful that you don't end up overheating the chip. So this particular one, even though it has thermal protection, I still wanted to calculate and make sure that I wouldn't overdraw in terms of my current draw for my circuit load. So a couple calculations you do. The chip itself can handle 125 degrees Celsius. That's its maximum operating temperature. And let's see, if I remember correctly, it is, without the heat spreader, there is about 50 degrees Celsius per watt worth of heat dissipation that this chip can handle. So we're talking about 2.5 watts worth of power that can actually go through. Now power is current times, so PIE. That's what, current times voltage, right? Okay, well let's say that it is. I will make graphics and I will make sure they're accurate. But what you want to do then is you want to take the difference. You want to make sure that you have less than 2.5 volts worth of power, worth of power going through this. So you do the 2.5 volts equals the voltage difference, which is the amount of heat that will be released, times, I believe it's X. And that shows you, for any given voltage, you have max current that can come out. Does that make sense?
Mm-hmm.
I think that makes sense. It'll make sense more when you see the numbers. So you'll see here that I've taken the difference of, taken 2.5 equals 27 minus the output voltage. Okay, taken that difference, which is going to be released as heat, and then multiplied it by X, and then solved for X. So when you solve for X, what you get is as your output voltage increases, you'll see how much current your power supply can handle and can allow your circuit to draw. Okay, I think that sounded like it made a little bit more sense. So these calculations, which is a very pretty graph, are the most conservative, I would say. I didn't account for the heat spreader in my calculations, but apparently the heat spreader make a big difference.
All right, so if you want any more details on anything that we've covered today, you can find out more information at tymkrs.com. You can follow us on Twitter to get links to our stuff as it comes out. Every day on Twitter at tymkrs. There's lots of project information on the forums. And if you need help on your project, go to the forums too. There's links to all that kind of stuff on tymkrs.com. So this week, one thing that we wanted to update you guys on is that we picked up a large collection of sheet music from, I'd say about the 1870s through the 1920s.
Yep.
And we're going to be working on getting this stuff framed and prepared as decoration for the studio.
Yep. Check this out. Men in Affairs. President Roosevelt surprised and pleased the sailors when he went on board the battleship Missouri to witness the target shooting by sitting at the table with the tars. And let me find another good one.
It's music that was clipped out of a newspaper, so the back of it has all sorts of news from the day.
Check this out. Plans for an international exhibition at San Francisco not later than 1913 is already being seriously considered. It will celebrate the 400th anniversary of the discovery of the Pacific by Balboa. It is also hoped that it will celebrate the opening of the Panama Canal. The exhibition will probably be called the Pacific Ocean Exposition or Fair, and Congress will be asked to contribute largely to its interests.
I want to get me some
Isn't
wonderful
that crazy?
bargains in guns and sporting goods. $2.95 for a single barrel shotgun.
You need some physic.
Hell yeah.
Let's get some physic.
All right, guys. Thank you for watching. We'll be back next week.
Yes.
Bye.
We post videos all the time, so don't forget to subscribe and follow us on Twitter at TYMKRS.